You see this right here? This is an IP camera. It's your typical IoT device. In this video, we are going to extract the firmware from this device, and we're going to reverse engineer it. So we're going to get started with the video. So to speed things up a little bit, I did remove the actual board from the outer housing of the IoT camera. When you get the camera out of the housing and you disconnect everything from it, this is what it looks like. There is also this piece right here that I went ahead and removed because this is not needed. So we'll put that to the side. And this is basically what we have right here. Standard IP camera, typical IoT device. This is what the back side looks like, and this is the side that we will be focusing on in the video. And if we can get a little bit closer here, you can actually even read the name off of the main chip here. So here is the CPU. Here's the main chip on the board. This is where the micro SD card goes. Here's a reset button. And the chip that we are going to be attaching the SPI flash memory programmer to is going to be this chip right here. It actually has a green mark on it. And typically you know which chip is the SPI flash memory chip. In this example, we have what appears to be two identical chips on the same board. They both have 4 legs on each side. They are both the same size. So how would you know which one is which? Well, you could just try each one and just use trial and error. But typically, the one that is closest to the CPU is going to be the SPI flash memory chip. And in this example here, they've further made it identifiable for us by putting the green line on it. So this is the one that we are looking at, and you can actually see that there is a little dimple on the corner of that chip. We want to make sure that the red line on the ribbon cable is going to the leg that is marked by this dimple. Okay, so let's briefly talk about the tools that we are going to be using. And inside of this tool bag, I have my go-to hardware tools for reverse engineering and hardware hacking. Of course, we have to have the multimeter, which I primarily use for determining the ground pin by doing a continuity test. And then over on the right-hand side, we have a handful of different tools. Up here at the top, I have a Raspberry Pi debug probe that is designed to work with the Raspberry Pi. I have my logic analyzer. I have my USB to TTL adapter. And finally, we have our CH341 programmer, also referred to as an EEPROM BIOS programmer. And this is what we are going to be using for this video. So here is the BIOS EEPROM programmer without anything else attached to it. And then here is the chip clip that is attached to the ribbon cable. This is what I call it, is a ribbon cable. There might be a different name for it. Feel free to correct me in the comments. And then at the end, you have one of several adapters. Once again, that's what I'm calling it. There might be a more appropriate name, and if so, feel free to correct me in the comments. So what we want to do is we basically need to attach the adapter and the ribbon cable to the BIOS EEPROM programmer. And you see that there is this lever right here. We push that up to basically open this up. that will allow us to insert the adapter inside of it. Now what I've done is I went and made this easy for myself, and I've actually marked both the side of this and this so I never forget which way that this goes in, because in the past I have confused myself as to which way it needs to go. So I'm just going to align the marks that I have previously made, and this is what it looks like connecting it. Let's just put it in like that. You can see from the side that's what it looks like. And then to secure it in place, I pull that lever back and that locks it. Now I can't pull that back out, and it is locked in and we are good to go. This is probably the trickiest part of this whole process. It's going to be a little finicky. You have to make sure all of the contacts on this chip clip here are connected and touching the legs on the side of the SPI flash memory chip. And once again, there is that dimple in the corner of the chip, and you want to make sure this red line on this cable, which is running to a specific contact inside of these plastic jaws on the end of the chip clip, you want to make sure that that red one is the one that goes over the leg where that dimple is. Okay, I feel pretty confident about that. Let me go ahead and give you a close-up of what that looks like. There's a side view of the chip clip connected to the flash chip. You just want to make sure that all of those contacts are in fact touching the legs of the flash memory chip. Okay, so we have the chip clip properly attached to the SPI flash memory chip on the board of the camera, and you can see the cable is running into the EEPROM programmer. We have that connected properly. The EEPROM programmer is connected to a USB cable. This is something that just makes things a lot easier so that you have more room to handle the device, and you don't have the EEPROM programmer plugged directly into the side of your computer, whether it is a laptop or a tower. It just makes things much easier. So the USB cable extender is running from the EEPROM programmer around my desk, and ultimately it's coming back over here into the side of my laptop. And on our laptop we are using Kali Linux. So let's go ahead and go down to the command line, and we are going to extract the firmware. First thing that I'm going to do is I'm going to create a directory to store the firmware and any other things that I'm doing. I will call that directory Mercury, because that is the name of this camera. CD inside of the Mercury directory, and we are going to use the flash ROM utility. If you do not have it installed, it's very easy to install on a Debian-based system. Just run the command sudo apt install flash ROM. We can pull up the help menu for flash ROM by running flash ROM -- help. The main thing that you are going to need to know is what kind of programmer that you are using, because there are several. The one that I am using in this video is a CH341A_SPI, and you can see that that is in this list. Once you've identified the programmer that you are using, you can go ahead and execute the first command. We are going to run the command flash ROM with a -P for programmer, and we are going to specify the name of the programmer, which is CH341A_SPI, and hit enter. the main thing that we are looking to get from this is that it does correctly identify the flash chip. You can see that it has found a Giga device flash chip, and here is the name of the chip. Now, in the past, I have had some issues when trying to run the flash ROM command and specifying the name of this chip because of the brackets that letter B falls inside of. So I'm going to make an attempt here, and we might have to do some trial and error on this. So I'll do -C for chip. I'm going to give it the name of that chip, and I am going to put the brackets in there, but I'm going to close everything in single quotes and see if that will allow us to run the command. And finally, I will do a -R for read, and we are going to have to give the file a name because it's going to not only read the contents of the flash memory chip, but it's going to save the contents to a file. So we will call that file mercury.bin, and I will hit enter. And it is reading the flash. So one of the key takeaways from this is that you have to get the syntax right, obviously, but putting the name of the chip in single quotation marks allowed me to get around any previous syntax errors that I had come across. So we're just waiting for it to finish reading the flash. Should be momentarily. All right, and it has finished. So let me clear the screen. We'll do an ls, and we now have a firmware image called mercury.bin. Let's go ahead and run ls-lh to get the size and human readable format of this firmware image. And it is 8 megabytes in size. All right, so this is wonderful. We have now extracted the firmware from this IoT device, this IP camera. Now what? So now that I have the firmware image on my machine, I am actually going to transfer machines, and we are going to pick back up in this video after I have transferred the firmware image over to my main machine here. So at this point, you might be saying to yourself, well, you know, that's great, Mr. Fresh, or whatever the hell you call yourself. You can extract the contents of the SPI flash memory chip, you have the firmware, etc., and so forth. But I want to follow along with what you're doing, and I don't have the firmware. Well, you can get the firmware. So I have a GitHub repository. I haven't been very active on it, but I'm going to become more active on it. Over here at github.com/Douglas Fresh Habian, I have 4 repositories currently as of the recording of this video. One of those repositories is called MerkCamFirm. If we click on that repository, we are brought to this page right here. And this contains the firmware that I dumped from the Mercury IP camera. The same firmware that I just dumped in this video. So all you have to do is do a git clone of this repository, and you have the same firmware that I am using in this video, and you can follow along and do everything that I am doing. So we come up here to the green box that says code. I'll click on that, and we are going to copy the HTTPS URL. I will go down to the command line inside of my terminal emulator. We will simply type in git clone and paste in that URL. This URL will also be in the description for the video. Once you have finished cloning the repository, you can cd into MerkCamFirm. And if we do an ls, we have a hashes.txt file. We have a README file. we have a user manual for the camera, and we also have a directory called Mercury. If I do an ls on that directory, this basically is storing some photos of the camera and the board. So for example, if I were to use the open command and I will just pick one of these JPEGs, don't remember which one is which, but we'll open one up and see what we have here. Let's take a look at the hashes.txt file. So inside of this file, we have 4 different hashes. We have an MD5 hash, a SHA-1 hash, a SHA-256 hash, and a SHA-512 hash. Basically what these are used for are to verify the authenticity and integrity of your firmware. What do I mean by that? Well, I will give you a more concrete example. Our firmware is called mercury.bin. This is what I've saved it as. If I were to use one of those 4 hashing algorithms, we will pick the MD5 hashing algorithm. I can run the command MD5 sum on that firmware image, and we get back an MD5 hash. This is the hash. I can then compare that to the MD5 hash that is stored in the hashes.txt file, and you can see that both of those hashes match. And we can do the same thing with the SHA-1, the SHA-256, and the SHA-512. That's just letting you know that you have the correct firmware image, that nothing has happened in transit, that nobody has modified it. Can open up the user manual, and this shows you what the camera looked like before we pulled the board out of the case that it was in. Gives you a description of it, the specs, the features, etc. and so forth. And the app that goes along with this is the Tuya Smart app. So it's just 2 pages. The main thing that we are looking at here is we have the firmware image that I have called mercury.bin. So we can do an ls-lh on that firmware image. We get the human readable size of approximately 8 megabytes in size. Before I unpack this with binwalk, there are a couple things that I like to do. One of those things is I like to run the strings command on the firmware image. With this one command and this one command alone, you can get so much information from a firmware image like this one, as well as many other ones. If I were to just run strings by itself on the image, we'll get back quite a bit of information, but this is not good because you can see a lot of the output. They're very small strings that don't really make much sense to us. So one of the things that I like to do is I run the strings command and I do a -n and I specify a number. The number I typically like to use is 10. And what this means is that it will only print human readable strings from the firmware image that are at least 10 characters or more. So now if I run that on the mercury.bin file, what we get back is an output that contains information that is more useful to us. We still have some strings, such as in this section right here, that seem to just be meaningless to us, but the majority of the stuff that we now have in our output is stuff that makes sense and is human readable. So we have boot arguments right here, we have what appears to be numerous function names, etc. and so forth. It might be beneficial to save all of the strings to a file. So I might, for example, rerun that command and redirect the output into a file called strings.txt. Now I can do a word count on that file and we'll see that it is 2,183 lines long. We can open that up and look at it. And from this point we could use grep and we could grep this file for particular strings of interest. So I might cat out the contents of this file and pipe the output into grep. We'll do a -I for case insensitivity, and we'll look for any string that has to do with SSID, as SSID would be the name of the network that this camera connected to. And as you can see, we get back a lot of information. And in red, we have the string SSID, and you can see that right here we have an SSID. So this would be the name of the Wi-Fi network that this camera was connected to. There's so much information here. It is unbelievable, and it's unbelievable that you can get all of this information simply from a firmware image and using strings, not even unpacking it, not going any further. We have the last date that this was updated. Right here we have a production server endpoint. Here is the vendor of the camera, which is Genie. Here is the device ID. Here is the camera model number. Here is the version of the firmware. Here is what appears to be some form of an account number. Absolutely incredible. We could also use grep directly on the firmware image. So I will do grep with a -A, an I, and a B. The -A will tell grep to treat the firmware image as a text file. The -I will use case insensitivity, so that means that whatever string we grep for, it can be in upper or lower case, and it will find the string. And the -B is to give us back the byte offset for where the string is located. So we will look for any strings that contain the word root. And we are running the grep command on the firmware image that is called mercury.bin. So if we take a look at the output, you can see that we get back several hits. In green, we have the byte offset. Here is the first example of our string of interest, which is root, and there are several instances after this. Each time you see the green, this is the byte offset for that location for that particular string. And I will give you one more example. So we can run the same command, grep with a -A, I, and B, and this time we will grep for the string pass. And this obviously could show up for many reasons, one of those being anything that has to do with passwords. And we'll hit enter, and once again we get back several hits, and the first thing that I see pertains to password information. Once again, over here on the left in green, we have the byte offset where the string is located, and we have several hits that come back. If you made it to this point in the video, thank you so much for watching. If you haven't done so already, please subscribe to the channel, like the video, post a positive comment, and as always,
stay fresh.
We'll see you in the next one.